Assalamu alaikum students. In this lecture number 13 we will discuss about the production of neutrons from the neutron physics chapter in your textbooks. So why it is important to study about the production of neutrons or detection of neutrons in the next lecture? Because the neutrons carries no charge, and it is they have a very slow neutrons have very high cross section for the nuclear reactions and more favorable for nuclear reactions and fission process. So it is important to study about their production because as they carry no charge, it's difficult to detect them. Also, it is difficult to produce them. So we must do some nuclear reaction to produce them or detect them. So in this lecture, we will discuss about the basics of neutron physics and its production. It is important to know about the production and detection of neutrons as they carry charge, as I told you, and faces no Coulomb barrier. So this is the most significant motivation. So due to its chargeless nature, it is favorable in many nuclear reactions as compared to charged particles such as proton or alpha particles. However, it is difficult to produce, accelerate, and detect neutrons. Acceleration is not so easy, so we can produce or end up with a fast neutron, and we can slow down them by using some more techniques. So we need to do nuclear reaction for the production and detection of neutrons. So properties of neutron: its symbol is small n. It is chargeless particles, carries no electrical charge. It is fermion and obeys Pauli exclusion principles. Its intrinsic spin is 1/2. It is a composite particle composed of 3 quarks, discovered by Chadwick in 1932, who also received the Nobel Prize in 1935. It strengthens the binding energy of nucleus as compared to protons because it carries no charge. It interacts via electromagnetic forces and also by nuclear forces. So even slow-moving neutron can penetrate the nucleus and initiate nuclear action because it faces no Coulomb barrier. So it can be produced by a variety of nuclear actions. There are some thermal neutrons. If they have energy equals to 0.025 electron volt to 1 electron volt, they are called fast-moving neutrons if their energy is between 10 kiloelectron volt to 10 mega electron volt. So there are some thermal neutrons, epithermal neutrons, slow neutrons, fast neutrons, as you can see on the slides. So slow neutrons have high cross-section area and more favorable than fast neutrons. A neutron contains 2 down quarks with a charge of -1/3 E and 1 up quark with a charge +2/3, and if we add up these charges, we'll end up with no charge. So like protons, the quarks of the neutrons are held together by strong force mediated by gluons. Antiparticle of the neutron is antineutron. So in Brauskirk in 1956, he discovered the antineutron after the antiproton discovery. The free neutron has a mass of this 9395614 electron over c square, and or it can be written in kg and amu. So sources of neutrons. So how can we get the neutron beam? The beam of neutrons can be produced by a variety of nuclear reactions. We cannot accelerate neutrons because they carry no charge. However, we can start with high energy neutrons from the nuclear reaction and reduce their energy through collision with the atoms with the various materials, and then we can use them for further nuclear experiments. This process of slowing of neutrons is called moderating. The neutron is essential to the production of nuclear power or nuclear reactor. With the discovery of nuclear fission in 1938, it was quickly realized that if the fission event produced neutrons, each of these neutrons might cause further fission events in a cascade known as the nuclear chain reaction. There are many many other sources of nuclear reactions, then famous ones which are listed. H3 plus deuterium gives you a helium plus neutron. If you have a neutron in the product, then this reaction can be used as a neutron source. However, for the experiment, if you need a continuous supply of neutron or neutron beam, you must continuous reactants in your pocket. So alpha beryllium source is also very famous. It is a typical a particle from a radioactive decay strikes a barium a nucleus, and a neutron can be released. For if you mix a long-lived alpha-emitting materials, means we need alpha continuous alpha beam to produce continuous neutron beam. It means we need some alpha emitting material, alpha decay material, means radium and barium, and which will decay in alpha decay, and we will get helium, which we can strike on the beryllium, and we can get a constant rate of neutron production, and the production rate is 10 to the power 7 neutrons per second can be achieved, and the Q value is quite high for this fraction, 5.7 mega electron volt. Photoneutron source in which we bombard our beryllium source with the gamma rays, and it changes to isotope of beryllium plus neutron. So if we want a continuous supply of neutrons in this through this process, we need a continuous supply of gamma rays which are striking on the beryllium source, and the production rate is 10 to the power 6 neutrons per second for each curie of sodium. Sodium is the source for the gamma decay for the continuous supply of the neutrons via gamma continuous supply. So its Q value is 0.8 mega electron volt. The advantage of photo neutron production is that we can get neutrons more nearly monoenergetic of same energy, particularly if the photon source is nearly monoenergetic. So fission reactors is also itself is a common source of neutrons. So from the fission reactor we can take as a continuous supply of neutrons, because in the one reaction we get 2 to 3 neutrons per fission. So the production rate is 10 to the power 12 neutrons per second, and the average energy of these neutrons is 1 to 3 mega electron volt. So these neutrons from the fission reactors can be useful for doing some other experiments, such as neutron diffraction, which is very important experiments for magnetic materials. So in this lecture we talked about the sources of neutrons. So there are some other sources of neutrons. Every nuclear reaction which contains neutrons in the product can be taken as a neutron source. However, to select a particular neutron beam with a particular energy, we must know about the Q value of the nuclear reaction before starting the experiments. So thank you, students. I hope you have understand and motivated well to read more from your textbook. Thank you.